Svante Janson is going to give us his second lecture on nice things discovered in books in the library.
So I decided today to talk about random graphs and leading up to some results on a random cluster model, which you've heard mentioned here, at least in Alan's talk. But let me begin with something simpler. I think I can put it over here. It's a random graph which I usually denote G and P. So n is the number of vertices, and then P is the probability between 0 and 1. So that's just the probability of having an edge between any given pair of vertices. So you do that independently for all pairs of vertices. You flip a coin, probability P of getting an edge. So note here that the important feature here is that this model is completely homogeneous. There's no difference at all between the different vertices or anything like that, which distinguishes this from models like percolation or other lattice models where you have some kind of geometry. You can say that the standard percolation model, you do exactly the same thing, except that you start with vertices which already are on a lattice, and then you only do this, put in edges, possibly put in edges for next neighbors. Or you could more generally start with any graph, really, and then you only look at the edges in the graph you start with, and with probability P you keep them, and with probability 1 minus P you remove them. But if you didn't have an edge to start with, you'll never get one. But as I said, I'm not going to talk about those models. To me, they are much more difficult when you have some kind of geometry involved, and the typical thing is that there is no geometry. So everything, every structure you see here is created by the randomness. For a physicist, this means that this is what's called a mean field model. Just
So you do have a geometry. You have the geometry of a complete graph.
Okay, yes. Yes. So you can write down here, say, the probability of having a certain edge set E is therefore, so you have, so a specific edge set here means that you have this number of edges, so probability P of getting them, and 1 minus P of not getting the others. So many are there, n choose 2 minus E. So since I later will talk about the random cluster model, let me also introduce that, or rather repeat it, since it was defined a few days ago here. So random cluster model. Again, this is the random cluster model on the complete graph with no geometry involved. I mean, we have G and P. We have a second or third, whatever it is, parameter Q. And now we have instead the probability of edge set E is, we take P to same thing for the edges, but we also add a factor of Q raised to the number of components. And then now this will not sum up to 1, so therefore we have to divide this by a normalizing factor, the partition function. So as I said, this is now for the complete graph. Again, people often study random cluster model on a lattice, so this is then for physics would be the mean field version of that. And as Alan explained, and I'm not going to repeat that, the Fortin-Kesslin correspondence says that this is more or less equivalent to the Q-state Potts model. So again, now Q-state mean field Potts model on a complete graph. You see that the G and P here, random graph, this type of standard random graph, is the special case when q is equal to 1. That means it corresponds to a Potts model with q equals 1, which means that you have only one choice for all your spins. So that's not very interesting for a physicist, but you'll see that there's a lot of mathematical interest in this model nonetheless. I should think that's enough about random cluster model for now. So if we go back to GMP, this type of random graph is often called the Erdős-Rényi random graph because this and a close analog of it, where you instead of specifying a probability specify the number of edges but still uniform of all possibilities. They were studied by Erdős and Rényi in a series of papers around 1960, which started the theory of random graphs. Now there are lots of other models of random graphs also. I may mention a few of them later on perhaps, but this is somehow the simplest one. It's often too simple for various applications. That's one reason why one wants to study other models too, but at least it's first one to where you want to study various things. And the general game in random graph theory is that you, at least if you are a combinatorist, you take any properties that a graph may or may not have, and then you investigate whether this random graph has it with or not, or with what probability it has. And typically all work here is done asymptotically as n goes to infinity, and then maybe you want p to depend on n, or maybe not. I mean, you could, for example, let p be equal to a half, which is very nice because then all these probabilities are the same. So it's just a uniform probability, uniform distribution over all labeled graphs. So that's natural in some cases, but usually you want this parameter, and as I said, often you really want it to scale it, want it to go to 0 as n goes to infinity to find interesting things. And what I'm going to speak about more precisely is one important thing, namely the structure of the components here, and especially the giant component. So let's take a let's redraw a random graph again here. This is maybe an instance of GNP, but you should think of n as being millions of vertices rather than whatever this is, 10 or something like that. And of course the graph, as any graph, can be decomposed into its connected components. And now you realize that it's very unlikely to have two very large components, because that means that you have two large sets of vertices and no edges at all in between them, and that doesn't seem very likely. And indeed that is the case, and it can so it can be shown that you have either you have only small or rather small components, of course many of them, or you have one big component and then maybe also a lot of smaller components together with it. So I will not give the most refined possible results, but the main thing here is when is this transition from only small components to one big component. And of course this is monotone in p. I mean, if you increase p, that means that you get more edges, so therefore graph will be more connected. And it turns out that the right range here is when p is like a constant over n. So we have a basic theorem which goes back to Erdős and Rényi. So if p is like constant, which today I'll call lambda over n, I'll say equal to maybe, then we have two cases. If lambda is strictly less than 1, all components are small, and without being too precise, say typically order of logarithm of n are the largest ones. Whereas if lambda is greater than 1, one component is large, roughly some theta times n. Positive constant here, which of course depends on my lambda. The rest small. Again, the others are at most log n. Most of them are even smaller. And you see, I haven't said exactly what happens when lambda is equal to 1. And there, of course, it's more sensitive. First of all, it's not perhaps so important what happens exactly p is 1 over n. You could think of 1 plus some little o 1 over n, and then it depends on how it approaches 1. Result, if it is exactly 1 over n, then actually the largest component is like n to 2/3. And there are several components of that size. But for a big picture, one can study that in great detail, and I've contributed to that, as many others have. But the big picture is this: we have a kind of phase transition at lambda equals 1. So theta here is theta of lambda, and it satisfies a nice equation. So theta, let's see, 1 minus theta lambda is e to minus, lambda times theta. Lambda. So an implicit equation. If lambda is less than 1, it's easy to see that there is no positive solution here. Theta equal to 0 is trivial a solution. So you can define theta of lambda as 0 for lambda less than 1. So theta lambda is 0 for lambda less than 1, and the unique positive solution to this thing for lambda greater than 1. You want to be very precise. And that means that it will look, if you draw a picture, it will look something like this. 1, constant 0, and then, of course, theta is always bounded by 1, since it's a fraction of vertices in the giant component. And you'll see that this function theta is, of course, nice and analytic because of the implicit function theorem, except here at 1, where you have it is continuous, but you have a jump in the first derivative. So it's a second-order phase transition in some sense. I mean, it is not exactly the same sense as the typical phase transitions in statistical mechanics, where you have an infinite model. In this case, you have these finite models. You have finite n, and then you take a limit. But you get this function in the limit, and it's analytic except at this point lambda equal to 1. So that's the justification for calling it a phase transition.
So this exponential result that holds all the way for lambda larger than 1?
Yes.
So no such thing as a power law?
No, exactly. And I'd like to try to explain why we have such a
So in physics language, the critical exponent here is 1, right? You don't get a cusp.
Yes, that's right. Quite right. You mean you can easily you can just by making tail expansion, you can make asymptotics here and see, I think the derivative is 2 if I remember correctly. So it's some positive finite number. So that's, as you say, critical exponent is 1, which makes it less exciting than some other results. Now there is there are many proofs of this, many ways of proving it. I think the original proof was done by counting small components, which are mainly trees, using generating functions and so on. So that was combinatorial way of doing it.
I'm sorry, in case 1,
yes.
All components are small.
Yes.
And is there a statement they're mostly trees?
Yes, I haven't written it, but they are mostly trees. There is a...
They're mostly trees. There are few unicyclic.
Exactly. There are few unicyclic components and no with more than one cycle. And few in this case means big O1, or rather the expected number of them is big O1 if you should be very precise, since everything is random. So when I write big O, it has to be interpreted in a probabilistic way. But remember, I'm the probabilist here. If I'm a bit sloppy today, no one else will notice it. Again, the case when lambda is equal to 1 is the most complicated one in some sense, because then you will have more, still not very many, but more than big O1 of unicyclic components, and you may have more than one with one cycle, 2 or 3 or so. There is a nice result there if you construct a graph by adding edges one by one instead of taking a fixed p as I do here. You can ask if it will it ever happen throughout the evolution that there is more than one component with more than one cycle. Of course, when you start, you have no components with cycles at all, and at the end you have one big component containing everything and lots of cycles. As I said, it's easy to see that in this range, take a fixed p, in this range you will have no, meaning asymptotically, you have no component with more than one cycle at all. And in this range, only the largest component, giant component, has more than one cycle. All the others don't have it. But
I'm sorry, what is this evolution means what? You put all of the n-2 edges in a random order.
Exactly.
And then lambda equals 1 corresponds to putting n edges.
Exactly. So that's, you can say, the stage when you look at it at time n, so to say, or you have this lambda or equal to 1, or you can scale the time in a nice way. So in that way you can think of this as evolution with lambda increasing from 0 up to infinity, or n, or whatever you'd like, and see what happens. Yes?
So is the statement all components are small must be taken in a probabilistic sense also?
Yes. So to be
so how is that defined?
To define this exactly, I would.
Isn't it just with probability that approaches 1 as n goes to infinity?
Well, but there is some subtle. I must say I'm not quite sure. This could be. There's one weak and one stronger version of this in probabilistic terms, and I'm not sure which one is true. A certain weak one is true. I'm not sure if the stronger one is also. The question has to do with the meaning of this big O in probability. So the stronger version is that there exists a constant, so that the probability of having more than that constant times log n goes to 0. The weaker version is that for every epsilon there is a constant, so that the probability of having larger than this constant times log n is less than epsilon for all n. And I have forgotten which one it is in this case. I think it may be the stronger one, but I'm not sure. In some of these results, certainly you have to use the weaker version.
Also, the other question, is theta asymptotic to anything when? No, is it asymptotic?
It's asymptotic to 1. Because when you have, with high probability, when you have high edge probability, you get almost all vertices in the giant component. Which is easy to see from this equation also, of course, but I mean it's very intuitive. But I was going to say here, just as a curiosity, if you do this evolution and you look at the probability of never having more than one component with more than one edge, it converges to 5 pi over 18. For reasons that I don't really understand, but to go back to a main theme here, a much more important thing, I want to explain the probabilistic idea of what I now regard as standard probabilistic proof of this thing, and that is a branching process approximation. We'll start with a single vertex. Well, we have n minus 1 other vertices, which it may potentially be connected to, and we have probability p for each one of them. So the number of edges here is binomial n minus 1 p with these parameters. And remember now that p is like lambda over n. So this is roughly a Poisson distribution with mean lambda. Now, for each one of the neighbors we found, if there are any, we then go on and look at their neighbors. So that's basically given by the same thing, except that now we've used a few vertices. We certainly, there's no point in going back, and also we should not investigate edges to the other ones we've found. But there are very few, so it's still n minus, in this case, n minus 3. So basically we add new number of Poisson lambda neighbors each time. So for each vertex we found, we find a new family of Poisson lambda. And that means it's a standard time, simplest standard branching process, Galton-Watson process. So this is now, meaning the limit, asymptotically. Galton-Watson process, maybe I should say asymptotically is better. With Poisson lambda of spring distribution in each generation. Of course, you can't do this forever because the Galton-Watson process maybe continue forever, infinite, whereas in the graph we know we start with a finite n. So at some point this approximation breaks down when you've used up too many of them. But nevertheless, the idea here, and that is rather easy to make rigorous, is that if this branching process lives forever, that corresponds to having a large component where you start, the point to start with. And if it dies quickly, well, then the component is small. So therefore, the question is whether such a branching process has a positive probability of continuing forever. And that's a well-known standard thing in branching process theory. It has, if and only if the expected number of children in each generation is at least 1. Well, you'll see immediately if the expected number is less than 1, then it will certainly die out quickly. And it's not surprising that that it will live on forever with positive probability. If the expected number is greater than 1, then the expected number in each generation will grow exponentially. And of course, you can always be unlucky and die out in the first 1 or 2 few generations. But if you survive in the beginning, you start getting large number of elements, then you have a very large probability of continuing forever. So that's a well-known fact that this lives forever with positive probability if and only if the expected number now, which is lambda, is greater than 1. So that is proof, if you fill in the details, of what I've written here. If lambda is less than 1, this will die out quickly, which means that the component will be small. And if lambda is bigger than 1, you have some positive probability, namely exactly this theta lambda, of living on forever, which, as I said, corresponds to being in a big component. And then you have to just translate that a little and say that if you take, here you start with one fixed vertex. You pick a vertex in the graph, and if that now has probability theta lambda of being in a big component, well, then that means that the fraction theta lambda of vertices have to be in a big component, which is exactly what I've said here. And we can now also understand this thing. It comes again from the branching process. That's again standard branching process here. You always have a functional equation of this type. And the reason is this. Here we have, start with a point. What's the probability that it will, the branching process will die out? Well, by definition, it's 1 minus theta, since theta was the probability it lives forever. But you can also think of it this way. You have a number of children, which is Poisson lambda. Each child has a probability theta of having an infinite number of descendants. And so, therefore, 1 minus theta of not having it. So that means if we only look at the number of, say, surviving children, ones with an infinite number of descendants, we have this Poisson number of children, but we keep them only with probability theta. And now it's a well-known property of Poisson distribution that if you thin them out in that way, you'll still get Poisson, but now you have to with parameter theta times lambda. So the number of surviving lines of descent is Poisson theta times lambda. So probability that that is 0 is e to minus that thing, which is the right-hand side. But that's, of course, probability of having no children with infinite lines of descent is the same as the probability of you're not having it yourself. So that gives this relation. Now, as I said, there are many other models of random graphs, and in several of them you can do a similar branching process argument to find out whether you have a giant component or not under suitable conditions. So I just want to mention briefly one of them, which is quite general.
So this
Yes?
argument works even though the branching process approximation is a very bad approximation late in the stage.
Yes.
If you're in the percolating region.
Yes.
Not the
Yes.
greatest one.
Because
Nevertheless,
it
it gets correctly, if you make the translation, that branching process telling you an infinite component translates into GNP having a giant component, it gets the probability right.
yes, because you can say that it only starts getting really bad when you have used up a small fraction of the, say, positive fraction of the all vertices. So that means basically that
Once you get there, you already have your giant.
yes, you have exactly. That's more or less how it works.
But it even gets theta exact.
Yes, and the reason why it gets theta exact is that you can say you can think of it this way. Suppose you know you have a giant component of some size theta, and then you pick a vertex at random. Well, then the probability of picking a giant component, of course, is exactly this theta. So therefore, the size of giant component has to be the same as the probability that a given vertex has an infinite, or infinite Galton-Watson process as in particle. So that's why you have equality of the probabilities there. I want to mention one of many generalizations of this random graph model, which I've studied myself with Bela Bolbach and Oliver Riordan here in Cambridge. So others have studied this or related models too. One of many and I'll tell you soon why I want to mention this particular model. So we take a kernel, which is called kappa, from 0, 1 cross 0, 1 to the non-negative real numbers. So let this be given. And I should tell you immediately that this case here, or rather this case here, corresponds to having kappa equal to a constant lambda. And now take points, say x1 up to xn, which are random, and IID is the right probability, independent and identically distributed, uniformly distributed, by the way, on 0, 1. So just pick n numbers on 0, 1 here. x1, x2, x3. And now what you do, you think of these as vertices or representing the vertices of your graph. And you do as before, you put in edges at random, but now you have different edge probabilities depending on these xi's. So add edge ij with probability, which is this kappa of x and y, except that I divide this by n. Sorry, yes, xi, xj. Divide by n. Well, if this happens to be greater than 1, you should interpret it as 1.
Kappa should be symmetric, I guess.
Kappa is symmetric, that's right. Should be measurable also. And this is one particularly interesting case, simple case is when kappa is just a, say, rank 1 product of, say, some function f of x times f of y. But you can do this more general in this way. And then one can do similar branching process argument. It now comes down to looking at what happens with a branching process with many types and infinite number of types, and you have this kernel representing it. So it's similar but much more technical. And the result here is that we have a giant component if and only if we have a certain integral operator with this kernel kappa, say t of kappa. The norm of this on as an operator on L2 is 0, 1 is greater than 1, where tau kappa f x is the integral of kappa x y f y dy. So in the if kappa is constant lambda, this is just integral operator is just a trivial thing, and you see it has norm lambda, and you're back in the old case. I think the reason, a bit surprised why L2 really would appear here, but I think that reason is that it's perhaps not really the norm but the spectral radius that's important, and it's the same thing here since it's a symmetric operator. But let me give you one concrete example here, namely kappa xy is 1 divided by the maximum of x and y. And there is a reason for this, because at least here I said we take the xi's random uniformly, but actually you can do this even more generally. This is natural in many cases, but another natural thing is to take them evenly spaced, 1 over n, 2 over n, 3 over n, and so on. Well, that imposes ordering, but if we don't care about ordering, it doesn't matter. So now if we take here xi as I over n instead of being random, then probability of edge ij now comes to, if you have a formula on top there which was 1 over n times kappa of I over n j over n, and if you put that in here, it's I want a constant here also, keep my lambda again, it's my lambda divided by the maximum of I and j, and somehow the n have mysteriously vanished, or rather they've cancelled. So you put in edges between I and j with this probability, and this has a very nice interpretation. Of course, you can think of this as adding vertices and edges sequentially. So when you add the jth vertex, you look at all previous vertices. Well, those are ones I when I is less, so this maximum is just j. And then, so that means that you add edges to them with probability lambda over j each, which means that on the average you add lambda, well, almost lambda, new edges for each one of them. So this is a version of one of Stanmore, but just now forgotten whatever it's called. Now this is a kind of version of the CH, K, and S model. It's not defined exactly the same way, but it's in a sense equivalent. So let's say roughly CH, K, and S. So I said the idea is that you add vertices one by one, and with each vertex you add, in this case not exactly lambda, but a Poisson lambda, number of edges to the previous vertices, and you choose them at random. It's not any kind of preferential attachment model, that's something different. So let me just say add vertices one by one, add let's say roughly Poisson lambda edges from each new vertex to randomly chosen older ones. Okay, so that's an example of the general formalism. You can put this kernel in here, get an integral operator, and it's possible to compute the norm of that, and one sees that the critical value here is lambda equals to 4/4. The value is lambda equals 1/4, because it turns out that this the norm of this t kappa is in general 4 times lambda. It's not completely trivial, but not too difficult to find that. But what I really want to say was something that Alan mentioned about rigorously proven phase transitions of infinite order. And this is one case here. Namely, if we look at the corresponding theta function, of course there's a theta function here too, theta of lambda. And in this case, it has been shown that if we now have theta of 1/4 plus epsilon, positive epsilon, this is now e to minus pi over 2 times square root of epsilon plus some small or big of logarithm of epsilon, as it says here. Now for epsilon positive. This was proved also by Oliver Riordan. It was a somewhat weak result proved by a joint paper we had with Vera Borubas first. So as you see, this function here, forget this small part, is goes to 0 very rapidly as epsilon goes to 0, and all certainly faster than any polynomial. All derivatives so are 0. So this function here is C infinity, but of course not analytic. Now I must admit there is a minor technical gap here which no one has, I think, even tried to fill in. So this is of course asymptotic. We have some error terms here. So I know that in this case theta looks like this. Here we have 1/4, and then it grows extremely slowly, so it's smooth. And then at the end it has to be asymptotic to 1 in any case. Now I would like to say that this is C infinity, but first of all I certainly believe that it's analytic except at the critical value. We have a general theorem for a result of this type, but that assumes something more about kappa, some technical condition which is not satisfied here, so we can use implicit function theorem in some Banach space. But I'm convinced that it's true here also. Some version of implicit function theorem should yield it. But the problem is rather here. So I know that the function itself is asymptotic like this, but that does not necessarily mean that the derivative is asymptotically like the derivative of this. In principle, this error term here could be fluctuating very widely, so that the derivative maybe doesn't converge, maybe it's discontinuous here. And now I certainly don't believe it is. I believe that all derivatives really are nice and continuous and so on, but that is not rigorously proven. The only thing that's rigorously proven is that we have an estimate of this type, which in a case I think justifies as an infinite order phase transition. But now I want to spend the last part of this week's talks on the random cluster model. So I've given you a definition there. And we asked the same thing here when I raised this theorem. I hope you know it. Is there a giant component or not? Big component. And that is, by the way, the question which is of main interest if you use this to study the Potts model. Because, well, remember the correspondence, Fortin-Kesslin correspondence, said that if you have the random cluster model like this, now I've erased my graph, it was silly, then what you should do is that you, for each component in the graph, you pick a spin at random from your q different values. And you do that independently for different components. But the point is that each component, all vertices in the same component have to have the same spin. Now that means that if you have only small components, you only throw out a small number of equal spins at the same time. And if, in particular, if you pick two vertices at, say, at random, doesn't matter since it's all the vertices are equal here, then with very high probability they are in different components and therefore they get independent spins. So you have asymptotically zero correlation. On the other hand, if you have a big giant component and you happen to pick two vertices both in the giant component, they have to get the same spin, which means that you will get a positive correlation function. And that also argument shows that there is a simple relation between the correlation function and the size of the giant component. I mean, they are essentially the same thing, just some different normalization. So therefore, the existence of a giant component and the size of it are exactly what you want to know for when you study a Potts model. And here I want to say, well, important thing here is perhaps not so much state a theorem, but rather I want to explain the main idea in the proof. Usually you try to avoid giving proofs and instead present results, but here I somehow think that the interesting thing is the trick used in the proof, and then it's more a routine thing to write down some formulas as a result. So this is something you can also find in the library here, but this one time I didn't get the book. It's described in Jeff Grimmett's book on random cluster measure, but it's also described in a paper by him and myself and Bela Bolobar some 10 years ago. So it's, you know, the idea is this. We have the random cluster model like this, and well, that means we have a graph. We have a lot of different components. Here we have a big one. Now we will do a random coloring of it. Let's see if I get the right colors, because the paper specified that the color should be red and green, so I think I'll try to follow that. So this is now G and PQ. Maybe I should have a white chalk also. So color every component. So first we have two things in right order. First we sample the random cluster models. We have an instance of G and PQ. And now we look at what components we have. Then we color every component is red with probability R, say. R is some fixed number we have chosen. Well, between 0 and 1, preferably, and green otherwise. And of course, we do that independently for each component. So maybe I start by choosing this one red, and then this one maybe is also red, then maybe we take a green one there, then let me take the big one, happen to be red. Next one maybe is green. And now let's look at the probability of getting some specific colored graph at the end here. And more precisely, we do that and look at set of all red vertices is of course random now, but if we condition on a specific set of red vertices at the end, that means we only look at all possible constructions here, possible outcomes that give exactly this set of red vertices. So how can we get that? Well, that means that first of all we should, when we take the random cluster model, we should not have any edges joining red to green. So we have only some components in this part which eventually is going to be red, and some others in the one which eventually is going to be green. Okay? But for all such configurations then, first of all we have this probability of getting exactly the edges we see. But secondly, we have to get the right colors, which means that we have to multiply by this probability r for each component which is becoming red, and 1 minus r for each one that's going to become green. So see now, probability of let's do this before. Let me go over here instead and say use the same thing. Probability of this edge of the colored, okay, let's say edge set E with colors, or given colors. Well, 1 over some z. If we have the same thing, exactly the same thing as before, but then times r to number of red components times 1 minus r to number of green ones. And well, if I combine these things, you can see that we can write this as this constant, the same p factors, but then we have rq to the number of red components, and 1 minus r times q to the number of green. And this means if I now, as I said, condition on having a certain set of red vertices and green vertices, this just decomposes a product of two things, from normalization factors. And what we see is that the red part is again given by a random cluster measure, but with parameter r times q. And the green part, we have same thing with parameter 1 minus r times q. And they are both independent. So condition on the set of red vertices being equal to v, say v1. See now, g and pq is, okay, the, how should I say this, is a union, whatever we call sum also, of red, maybe I should put it this way, g and not n1, say n1 is the order of v1. Same p, and the q, as I said, now becomes r times q. And independent, I don't use the independent really, green, make this a colorful thing. So it's n minus n1 left, and we have same p, and we have 1 minus r times q. And the main way we use this is that if we now are in the case when q is greater than 1, we choose r to be 1 over q. So then r times q here is equal to 1. So that means that this red part, well, it has a bit random size, but given the size of it, it is just a cluster model with q is equal to 1, which is the original Erdős-Rényi graph. And we know a lot about that.
And the random size has unknown distribution.
Yes, that's right. But we can, it has. At the moment, it's completely unknown. But I'll show you how you can now deduct things using that. Let me also say that we can get results when q is less than 1 by doing the opposite thing. If we start with q equal to 1 here, then the red part will have gn1pr. So if we now call r equal to q, we see that the red part will be a random cluster model with q less than 1. And now again it has a random size, which is a nuisance, but you can get results for GNPQ in that case. But let's now look at a physically more interesting case when q is greater than 1, and take r as 1 over q. Thus the red part is given, so conditioned on n1, is just gn1p. So we use this repeated. For example, suppose that that this random cluster model has two large components, size bigger than some small, well, not just small constant. Say we have two components bigger than n2 3/4. So we have, well, if that's the case, we have probability r square of coloring both of them red, which means that we would end up with two such large components in this graph. Now n1 is unknown, but at least n2 3/4 is at least n1 to 3/4. And we know that in GNP, as I said before, it's very unlikely that we have two large components. So therefore, as a result, it must be very unlikely here too that we have two large components. I'm running out of time, so I'll try to say this rather than writing it down.
And since you don't know n1,
Yes?
you don't know whether the resulting random graph is above critical or below critical.
That's right.
And lambda is n1p.
That's a problem. That's the main problem. But we can say a lot with it now. So first thing is that we have, so at most one component, say greater than n to 3/4. So that's the first conclusion, what I said. So let, again, say theta, let the largest component be theta n times n, say. I reserve theta for a limit. So theta n is really random here. This is number of vertices. So now what can happen is that the largest component is either red or green. Well, obviously, we know the probability is red is this and green is 1 minus r. But all other components, there are many of them that are all small. And there it's easy to see that the variance of the number of red vertices you get there is quite small, since all of them less than n to 3/4. So you basically have the law of large numbers telling you that a fraction r of all other vertices with small error is red. So two cases. We have probability r, largest component red. We have n1 is roughly theta n times n plus what's left is r times 1 minus theta n times n. And we have a large component which is theta n times n. or largest component green, then n1 is just like r times 1 minus theta n times n, and we have no large component. And now, since r is some fixed,
So why in the second case there's no large component?
pardon? Because if the largest component is green, we have only the other ones. All of them are at most n to 3/4 in size. So there is no other big component left. I mean, no
Well,
large
there's no large
component in the red
component.
part.
I
I
mean,
mean,
in the red part.
yes, in the red part. I'm talking about the red part here.
Yeah, okay.
So here is red part, everything. So the red part is the usual Erdős-Rényi graph, where I have either that case or this case. And actually both cases can happen now with some positive fixed probability. So both of these have to be compatible with the standard Erdős-Rényi theory. So for example, if we look at the last one here, that means that this has to be a subcritical case. So we see that so this is subcritical, which means that n times this lambda before. Now we have, since we change n, we should be a bit careful. But remember, it means that n1p has to be less than 1. And n1 times p here is this thing, r 1 minus theta n times n times lambda over n, and the n's cancel. So this has to be, well, at most 1. And r was equal to 1 over q, or 1 minus theta n times lambda is at most 1, or sorry, at most q. So we can draw one conclusion from that, for example, is that if lambda is greater than q, then this theta n cannot be 0, because it would violate this. Then theta n is greater than some, well, some positive number, whatever you get if you invert this, greater than 0. Everything I say now is with large probability. So this means that, so there is a giant component. If we look at the first case here, well, if theta n is equal to 0, so I mean there really is no big component, then we can't say anything more. But if this theta n really is some substantial positive number, we have a large component and we have this number of vertices, and we have the formula which maybe I erased already. So remember now, for Erdős-Rényi, we had 1 minus theta was e to minus theta times lambda. If we use that for the red part, use for red part when the largest component is red. So now theta should be this thing. Theta should be this thing divided by n1. So I have to be a little bit careful here. 1 minus theta n times n divided by n1, which is theta n times n plus r times 1 minus theta n times n. This should equal e to minus theta, again, this is theta n times n divided by n1. And lambda now is really, it's p over n. So it should be this thing. It's not p, sorry, no, not lambda.
It's p
sorry.
times n1.
Yes, no, what I should do, I should write it like this. Theta n times lambda over n, because lambda over n was the probability, which was p. This is the right way to do it. Now, since I'm changing n, it will get confusing otherwise. So this is theta n times n. This is what it will be. And n times p again is lambda. So if you do a simple algebra out of this, you'll end up with a formula E2 minus lambda, if I drop the subscript m, because that's what we're going to converge to, this thing, 1 minus theta, 1 plus q minus 1 times theta. So you see, if q is equal to 1, which it isn't, I assume it's bigger, but for q equal to 1, this reduces to the same formula as we had before. So this is the generalization of that for the q, for random cluster model for q greater than 1. Well, it turns out to be true for q less than 1 also. Now, of course, this again is solved by theta equal to 0 always. And question is what happens to this? And one can do some simple analysis. It turns out that if you can write lambda, solve for lambda here as a function of theta, and then we can solve this. Lambda is f of theta, where f is, you just write down what it is, logarithm of the right hand side here, 1 minus theta over 1 plus q minus 1 times theta, and then minus 1 over theta. That function looks like this. If q is less than 2, so if q is say between 1 and 2, it starts, you can see when theta goes to 0, it's easy to see that, I think it's easy to see this will roughly be q limit, so, and it will be monotonely increasing. If you take larger q, here we have q which is greater than 2, it starts down and then it increases, has a minimum. And so first, if we have the range now q between 1 and 2, then it means that if lambda is less than q, there is only possible solution 0 to this equation. So theta has to be 0. There is no big component. If lambda is greater than q, well, we have in principle two possible solutions. Here we have 0 or a positive value. But I've just shown you lemma somewhere that if lambda is greater than q, it cannot be 0. So it has to be this positive solution. So the correct solution is the one on the line here. Let me so I mean, now you should think of it going upside down. Lambda is parameter and you read off the value of q. I don't have time to draw a new picture. If q is greater than 2, then we see that when lambda is smaller than this minimum, 0 is own possibility. When lambda is greater than q, we know again that it has to be this positive value, which is then unique here. So then you have to make more detailed analysis, which fortunately had to do some real calculations. But to find the value where it jumps, so it's 0 up to some value in between here, and then it jumps to the largest value here. So now again, you should look at this from the reflect this picture and see that here you have a first order phase transition when q is greater than 2. But when q is less than 2, you have again a first order phase transition with this being continuous. And if you look at the derivative at the critical point, you'll also see that the derivative is continuous when q is strictly less than 1. So you have exponent 1, but you have a quadratic thing here when q is equal to 2. So you'll then get the exponent half, I think. Okay, I think I've, as everyone else here, spoken too long, so let me stop now. Yes?
Well, I have two questions about extensions of this. I guess the first is doable and maybe the second isn't. So the first is, now that you have the gross behavior, the natural thing is to now look in the finite size scaling window right around the transition. So for example, for the ordinary GNP, you would say lambda equals 1 is the transition. So you would say P is 1 over n plus x over, I think it's n to the 4/3.
Yes.
And then you try to compute everything as a function of x. And then I guess there are 3 different finite size scaling regimes depending on whether q is less than 2, equal to, or greater than 2.
Yes, and the one greater than 2 is the, we have first order phase transition, of course, is the most complicated one, where it's 100 jumps. Yes?
So that's that would be the first question, to try to
Yes?
characterize, to try to get formulas for everything of interest in the finite size scaling regime as a function of the variable x that parameterizes how you go through this window.
Yes?
Okay, that I guess is the one that's doable. But then the second one, I don't know if anybody has done before, make everything complex. Make your probabilities complex. Of course, they're no longer probabilities, but the partition function z is perfectly well defined. It's some big polynomial in P and Q. It's natural to look for its zeros in the complex plane. It's also natural to try to compute the limiting infinite volume free energy, limit 1 over n log z of blah, 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 for complex P or complex lambda.
As you may have guessed, even if I didn't say so, for real parameters I study here, you get that limit out of these calculations without much problem. But I think that if one wants to do that, one cannot use this nice trick, and that was the reason why I wanted to talk about this. We had this coloring argument here, which gave us a lot of things with very little calculations. And I should say that this random cluster model has been treated in some more detail, but I don't remember exactly what, by Luchak and Woodchuck. And they did some explicit estimates of partition function directly, and that's probably the method you have to use if you want to do it complex, except that everything is more complicated then.
Right, that's what I was wondering, whether avoiding this trick, there's just some direct combinatorial.
Yes, they did direct calculation, the estimating partition function, and got it with a lot of work, but I think in principle they're all straightforward.
It might be generalizable to complex
That's possible,
P,
yes.
or complex Q, but then you have to be very careful about cancellations.
Yes, exactly. Okay, no one else. Then I think we've done our work for this week. Oh, thank you.